Anatomy of a class. The programs we've written in previous examples have used classes defined in the Java API. You're talking about what we did for Chapter 3. Now we will begin to design programs that rely on classes that we write ourselves. The class that contains the main method is just the starting point of the program. True object-oriented programming is based on well-defined classes that represent objects with well-defined characteristics and functionality. Examples of classes. So here they're giving you some examples of classes, what their attributes are. The attributes would be the instance data and what their operations are. The operations would be the methods. You have a class for student, rectangle, aquarium, flight, employee. Some attributes for student is a name, address, major, grade point average. Rectangle is linked with color. Aquarium is material, length, width, height. Flight is airline, flight number, origin city, destination city, current status. Employee is name, department, title, salary. And some operations, which are the methods for a student, is set address, set major, compute grade point average. The rectangle, some methods for that is set length, set width, set color, and then some methods for the aquarium. They have their setters in there, but they also have compute volume and compute field weight. The flight, they have the setters for the airline and the flight number and determine status. And for the employee, they have some setters in there, but they also have some compute methods for the wages, bonus, and taxes. Recall from our overview of objects in Chapter 1 that an object has a state and a behavior. Consider a six-sided die, singular for dice. Its state can be defined as which face is showing. Its primary behavior is that it can be rolled. We represent a die by designing a class called die that models this state and behavior. The class serves as a blueprint for the die object. We can then instantiate as many die objects as we need for any particular program. A class can contain data declarations and method declarations. So they're showing you where the data declarations and the method declarations occur. The values of data define the state of an object created from the class. The functionality of the methods define the behaviors of the object. For our die class, we might declare an integer called face value that represents the current value showing on the face. One of the methods would roll the die by setting the face value to a random number between 1 and 6. We will want to design the die class so that it's a versatile and reusable resource. Any given program will probably not use all the operations of a given class. See rollingthedice.java and die.java. Here is the example they're giving in the lecture. It's similar to what I did in my die class, but I'm going to go ahead and read through this. So they have a class named Rolling the Dice. It has the main method, so this is a driver class. They declare two variables to hold a die object, and then they instantiate the die objects. They declare a variable for the sum, they roll the dice, and then they concatenate the object to a string. They roll it again, set face value, output that information. They get the sum, output the sum, roll the dice again, output the value, and output the sum. Now notice that they're actually concatenating the object reference variable. This is going to call the toString method. So here is a die blueprint class. They created a constant for max. Now I also made one for min. Now notice how they didn't make it a class variable. This is a constant, but it's actually associated with the instance of the object. So this is actually going to be associated with the instance of the object instead of the class. If you make it static, then it becomes a class variable. They have a constructor. In their constructor, they set the face value to 1. That's exactly what we did as well. They have a roll method. Their roll method is similar to what we did, except they're returning the face value through the roll method. So the roll method that I created, I did not return the face value. So they're randomizing the face value and then returning the face value. And then here's their setter. The setter that I created, I use an if statement. Here's their getter. And then here's their toString. For the toString, they actually converted the face value to a string and just used the toString in order to output that value. So the die class that they did contains two data values, a constant max that represents the maximum face value, and integer face value that represents the current face value. The roll method uses the random method of the math class to determine a new face value. There are also methods to explicitly set and retrieve the current face value at any time. It is good practice to define the toString method for a class. The toString method returns a character string that represents the object in some way. It is called automatically when an object is concatenated to a string or when it is passed to the println method. It's also convenient for debugging problems. Constructors. As mentioned previously, a constructor is used to set up an object when it is initially created. A constructor has the same name as the class. The die constructor is used to set the face value of each new die object to 1. We examine constructors in more detail later in this chapter. Data scope. The scope of data is the area in the program in which the data can be referenced or used. Data declared at the class level can be referenced by all methods. So what they mean by class level is they mean data outside of the methods. So I say terms like a class level constant. That's when I make a constant static, so the variable is associated with the class and not an instance of the class. Data declared in a method can be used only in that method. Data declared within a method is called local data. In the die class, the variable result is declared inside the toString method. It is local to the method and cannot be referenced anywhere else. So here's the toString method that they had for their die class. So what they're talking about is this result variable here in the toString method. It holds the value of the face value as a string, and then that value is returned out. So this variable can only be accessed within this toString method. And this is what they call a local variable because it's local to this method only. Instance data. A variable declared at the class level, such as face value, is called instance data. Each instance object has its own instance variable. A class declares a type of data, but it does not reserve memory space for it. Each time a die object is created, a new face value variable is created as well. The objects of a class share the method definitions, but each object has its own data space. That's the only way two objects can have different states. So whenever we instantiate an object from a blueprint class, whatever the instance data is what gets put into memory. The blueprint is the instructions for that object. So looking back at the die class that I created, here is the instance data. So every time we instantiate an object of the die class, a face value is going to be put into memory. So each instance in memory is going to have its own face value. So that's why we can have two die with two different face values. Now when I declared this min and max to be static, an instance of the die object does not have its own min and max. These variables exist only once, and it's for any object of the die class. So when I declared these constants, I declared them to be static. Now when I use static for my constants, that means that every instance of the die class will not have these variables in memory. These variables are associated with the class only and declared once, and all instances of this class will be able to use these values. Now all our method definitions are not in memory. They're in our blueprint. They're instructions that Java use in order to know how our object in memory should behave. So the only thing that gets put into memory is whatever our instance data is. We can depict two die objects from the rolling dice program as follows. So they have two die objects and they each have their own face value. Each object maintains its own face value variable and thus its own state. UML diagrams. UML stands for Unified Model Language. UML diagrams show relationships among classes and objects. A UML class diagram consists of one or more classes, each with sections for the class name, attributes, the data, and operations, the methods. Lines between classes represent associations. A dotted arrow shows one class uses the other, calls its methods. So here is a UML diagram for the example they did in the lecture. They have a class rolling dice. They have a class called die. There's no instance data associated with rolling dice. It only has the main method, but we do have instance data for our die. And then here are all the methods that we have for our die. Quick check. What is the relationship between a class and an object? A class is the blueprint of the object. The object is an instance of the class, and that's what we have in memory. We can have multiple objects from the same class. A class is the definition pattern blueprint of an object. It defines data that will be managed by an object but does not reserve memory space for it. Multiple objects can be created from a class, and each object has its own copy of the instance data. Where is the instance data declared? The instance data is declared at the class level. What is the scope of instance data? Instance data can be referenced anywhere within the class. What is local data? Local data is data that exists within a method and only can be accessed within the method. So here are the answers. So they say instance data is declared at the class level. What is the scope of instance data? It can be referenced in any method of the class. What is local data? Local data is declared within a method and is only accessible in that method.